There's a hole in the sun right now, not a metaphorical one, not a small one, a gargantuan tear in our star's atmosphere, stretching from pole to pole, pointed directly at Earth like a cosmic cannon. And while you've been sleeping, it's been firing. 700 kilometers per second of charged plasma, hammering our planet's magnetic shield for weeks. Coincidentally, or perhaps not so coincidentally, the Earth has been answering back. Magnitude 7.6 in Japan, magnitude 6.5 near Papua New Guinea. Deep ruptures releasing tectonic energy in ways that make seismologists nervous. The official position? Pure coincidence. But the data tells a stranger story. Stay with me until the end, because what's happening between our star and our planet right now might rewrite what we thought we knew about how this system actually works. You'll want to follow along as this solar anomaly unfolds in real time. Subscribe now, because the sun isn't finished with us yet. The connections we're exploring are just beginning to surface, and you'll want to be here when the pattern finally reveals itself. Right now, at this very moment, something massive has opened up on the surface of our star. If you could look at the sun through the right kind of telescope, what you'd see would stop you cold. There's a hole. Not a small one, not a typical one. A gargantuan chasm in the sun's atmosphere that stretches from the northern hemisphere all the way across the equator and down into the southern reaches. This isn't supposed to happen often, and when it does, Earth pays attention. This structure has a name in solar physics. Scientists call it a trans-equatorial coronal hole. The coronal part refers to the sun's outer atmosphere, that shimmering halo you see during a total eclipse. The trans-equatorial part means this thing crosses the middle of the sun, spanning both hemispheres like a scar. Coronal holes appear dark in certain wavelengths of ultraviolet light because they're regions where the sun's magnetic field has opened up. Instead of looping back on itself in neat, closed arcs, the magnetic field lines in these zones just shoot straight out into space. And when that happens, hot plasma escapes. The sun bleeds. What makes this particular coronal hole so unusual isn't just its size. Size matters, sure, but geometry matters more. Because this hole is positioned right on the solar equator, it's now rotating into perfect alignment with Earth. Picture the sun as a gun barrel and Earth as a target downrange. For the next several days, we're standing directly in the line of fire. The solar wind streaming out of this coronal hole is moving fast. We're talking 700 to 800 kilometers per second. That's nearly 2 million miles per hour. A river of charged particles, electrons and protons, hurtling through space and slamming into Earth's magnetic field. Now, solar wind isn't new. The sun always emits a steady breeze of particles. But coronal holes crank that breeze into a gale. And unlike solar flares, which are violent but brief, or coronal mass ejections, which are dramatic but sporadic, coronal holes are persistent. They can last for weeks. They rotate with the sunday. Every 27 days or so, if the hole is still there, Earth gets blasted again. It's like living next to a neighbor who occasionally opens their door and a hurricane blows out. You can't move. You just have to weather it. The immediate effects we know about are real and measurable. When high-speed solar wind hits Earth's magnetosphere, the protective bubble of magnetic field that surrounds our planet, it compresses. The magnetosphere gets squeezed. Charged particles funnel down along magnetic field lines toward the poles, colliding with atmospheric gases and producing auroras. The northern lights intensify. If you're in Canada, Scandinavia, or Alaska right now, the skies are probably dancing. But auroras are just the pretty side effect. The ugly side involves geomagnetic storms. Space weather agencies classify these storms on a scale from G1 to G5, with G5 being catastrophic. Most coronal hole events produce G1 or G2 storms, minor to moderate. Satellites experience increased drag. GPS signals get fuzzy. Power grids in high-latitude regions can see induced currents that mess with transformers. Radio communications get disrupted. None of this is apocalyptic, but it's not nothing. It's a reminder that we live inside a star's atmosphere, and when the star hiccups, we feel it. Here's where the timing gets interesting. We're currently in the declining phase of solar cycle 25. Solar cycles last about 11 years, marked by the rise and fall of sunspot activity. Solar maximum, the peak of the cycle, happened earlier this year. After the maximum, the sun doesn't just calm down smoothly. It goes through a messy transition. Coronal holes become more common and more pronounced during this phase. The sun's magnetic field is reorganizing, flipping polarity, and in the process, these gaps open up. But even for a declining phase, this coronal hole is abnormally large and unusually well positioned. The SETI Institute released imagery showing the hole's extent. It's enormous. It spans a significant fraction of the solar disk, and its transequatorial nature means it's directly facing us. Most coronal holes appear at higher latitudes, near the poles. They still affect Earth, but the geometry is less direct. This one is different. This one is pointed right at us like a cosmic spotlight, and the beam is made of plasma. So why does any of this matter beyond the auroras and the satellite operators scrambling to adjust orbits? Because space weather doesn't exist in isolation. Earth isn't a passive rock floating through the void. We're an active, dynamic planet with our own magnetic field, our own electrical systems, our own geophysical processes. And when the sun throws a punch, Earth responds. The question is how. The question is whether the response is limited to the upper atmosphere and the magnetosphere, or whether something deeper is happening, something we don't yet fully understand. Because here's the thing. While this massive coronal hole has been blasting Earth with high-speed solar wind, something else has been happening. Down here, on the ground, the Earth has been shaking. December 2025 has been a loud month for the planet. Seismically speaking, the Earth has been restless. And not just random background noise. We're talking about significant earthquakes, magnitude 6 and above, clustering around some of the most active tectonic zones on the planet. The Pacific Ring of Fire, that horseshoe-shaped belt of volcanic arcs and subduction zones that wraps around the Pacific Ocean, has been particularly active. And the timing? Well, the timing is what gets your attention. On December 8th, a magnitude 7.6 earthquake struck off the coast of Sanriku in Aomori Prefecture, Japan. That's a big quake. Magnitude 7.6 is major. It's the kind of event that triggers tsunami warnings, evacuation orders, and international news coverage. 4 days later, on December 12th, a magnitude 6.7 aftershock hit the same region. Then, on December 22nd, just 10 days after the Japanese aftershock, a magnitude 6.5 earthquake occurred near Papua New Guinea. These aren't minor tremors. These are significant releases of tectonic energy. Now, earthquakes happen all the time. The Earth is constantly adjusting, releasing stress along fault lines. The Pacific Ring of Fire accounts for about 90% of the world's largest earthquakes. So finding big quakes in Japan and Papua New Guinea isn't, on its own, unusual. But what catches the eye of seismologists is when you get clustering. When you see multiple high-magnitude events in a relatively short time window, it suggests something systemic. It suggests that stress isn't being released randomly, but in coordinated bursts. The crust is responding to some larger pattern of pressure. The Papua New Guinea quake is particularly interesting for another reason. It occurred at a depth of approximately 110 kilometers. That's a deep focus earthquake. Most quakes happen in the upper 15 kilometers of the crust, where rocks are brittle and can fracture. But deep focus quakes occur in the subducting slab, the oceanic plate that's diving down into the mantle. At those depths, rocks are under immense pressure and temperature. They don't fracture the way surface rocks do. Instead, they undergo phase transitions, sudden changes in mineral structure that release energy. These deep quakes are strange beasts, and they matter because of how they transmit energy. When a shallow earthquake happens, the seismic waves radiate outward, shaking the nearby region intensely. But deep earthquakes send seismic waves through the entire body of the Earth. These waves can travel thousands of kilometers with relatively little attenuation. They can interact with distant faults, transferring stress across tectonic boundaries. Some seismologists believe that deep quakes can influence the timing of shallow quakes half a world away. It's called stress triggering, and while the mechanisms are debated, the correlations are real enough to make people pay attention. So here's the sequence. Massive coronal hole opens on the Sunday. High-speed solar wind begins battering Earth's magnetosphere. Within days, a magnitude 7.6 quake hits Japan. Aftershocks follow, then a deep focus quake in Papua New Guinea. All of this in the span of 2 weeks. Coincidence? Almost certainly. Correlation doesn't equal causation. The United States Geological Survey, the USGS, is very clear on this point. There is no demonstrated causal relationship between space weather and earthquakes. The science does not support a direct link. Solar wind doesn't make faults slip. Geomagnetic storms don't trigger tectonic ruptures. That's the official position, and it's the position of mainstream seismology. But here's where it gets interesting. Not all scientists agree. There's a fringe of research, small but persistent, that suggests correlations between geomagnetic activity and seismic events. Studies have looked at ionospheric anomalies, disturbances in the electrically charged layer of the upper atmosphere, occurring near tectonic plate boundaries in the days before large earthquakes. Other studies have examined whether geomagnetic storms correlate with increased seismicity over multi-day windows. The results are mixed. Some studies find weak correlations. Others find nothing. The data is noisy. The mechanisms are unclear. And so the mainstream dismisses it. Yet the pattern is hard to ignore, especially when you zoom out and look at the broader context of 2025. This hasn't been a quiet year for the planet. Earlier in the year, an 8.8 magnitude earthquake struck Russia, one of the largest quakes in recent memory. Volcanic activity has been elevated across multiple regions. The Pacific Rim has been unusually energetic. And now, during one of the most pronounced coronal hole events of the solar cycle, we're seeing this cluster of significant earthquakes. There's a visual quirk to this story that's almost too strange to mention. The shape of the trans-equatorial coronal hole, as captured in solar imagery, bears an uncanny resemblance to the outline of Japan. It's Paridolia, of course. The human brain loves to find patterns, faces, maps, meaning in random noise. But there it is, on the images from the SETI Institute. A hole in the sun shaped vaguely, like the very island nation that just experienced a major quake. It means nothing. Probably. But it's the kind of coincidence that makes you pause. What we're left with is a story with two parallel tracks. One track is space weather. The sun is doing something unusual. A massive coronal hole is blasting Earth with charged particles. The other track is geophysics. The Earth is shaking in significant ways, releasing tectonic energy along major fault lines. The official scientific position is that these tracks are unrelated, and yet the timing nags at you. The clustering nags at you. And buried in the fringe literature are hints that maybe, just maybe, we're missing something subtle, something that doesn't fit our current models, something that requires us to ask questions we've been avoiding. Let's be absolutely clear about one thing first. The idea that solar wind directly triggers earthquakes is not accepted by mainstream science. It's not in the textbooks. It's not taught in seismology courses. The United States Geological Survey doesn't issue earthquake forecasts based on space weather, and for good reason. The evidence for a direct causal link simply isn't there. If you ask a seismologist whether a coronal hole can make a fault rupture, the answer is no. Faults rupture because of tectonic stress, period. The forces involved in plate tectonics, the grinding of enormous slabs of rock driven by convection in the mantle, dwarf anything the sun could throw at us electromagnetically. But dismissing the question entirely might be premature, because while direct triggering isn't demonstrated, the possibility of subtle coupling, of indirect influences operating through mechanisms we don't yet fully understand, that possibility remains open. And the physics, speculative as it may be, is at least worth examining. Start with what we know happens when high-speed solar wind hits Earth. The magnetosphere compresses. Picture Earth's magnetic field as a bubble, inflated by the pressure balance between the planet's internal magnetic field and the pressure of the solar wind. When a fast stream arrives, it pushes against that bubble, compressing the day side and stretching the night side into a long tail. This compression drives electric currents in the magnetosphere and in the ionosphere, the layer of charged particles in the upper atmosphere. These currents are enormous. We're talking millions of amperes flowing through near-Earth space. Now, electric currents generate magnetic fields, and changing magnetic fields induce electric currents in conductors. Earth's crust isn't a perfect insulator. It contains rocks with varying levels of electrical conductivity. Seawater is highly conductive. Magma is conductive. Certain minerals are conductive. So when you have large, fluctuating currents in the magnetosphere and ionosphere, those fluctuations can induce telluric currents in the ground. These are literally electric currents flowing through the Earth's crust. Telluric currents are well documented. They're monitored because they can interfere with power grids and pipelines. During intense geomagnetic storms, These induced currents can damage transformers and cause blackouts. The physics is straightforward electromagnetic induction. Faraday's law, high school physics, scaled up to planetary dimensions. So, we know that space weather can inject electrical energy into the crust. The question is whether that energy can influence tectonic processes. This is where things get speculative. One hypothesis, and it's very much a hypothesis, is that changes in electrical potential in the crust could affect the mechanical properties of rocks near fault zones. Rocks under stress can exhibit piezoelectric effects, generating small electrical charges when compressed. Conversely, applied electrical fields might influence the stress distribution in rocks. Could telluric currents alter the friction along a fault surface? Could they change the pore pressure in fluid-filled fractures? Could they provide the tiny nudge that tips a fault already near failure over the edge? Nobody knows. The experiments haven't been done at the scale that would matter. Laboratory studies on rock mechanics and electromagnetic fields exist, but extrapolating to real-world fault zones kilometers deep is a massive leap. And yet, the question persists because of the observational hints. Some researchers have found correlations between geomagnetic activity indices and earthquake occurrence rates over multi-day windows. The correlations are weak and inconsistent, but they're there in some datasets. Another proposed mechanism involves the ionosphere. The ionosphere isn't just a passive layer of charged particles, it's electrically coupled to the ground. There's a weak but real global electric circuit, driven by thunderstorms, connecting the ionosphere to the Earth's surface. Some researchers have proposed that disturbances in the ionosphere, caused by solar wind, could propagate downward, altering electrical conditions near the surface and potentially influencing pre-earthquake processes. This is known as lithosphere-ionosphere coupling, and it's controversial. The mainstream view is that any such effects would be far too weak to matter. The fringe view is that we don't understand the sensitivity of fault systems to small perturbations. Coronal holes are particularly interesting in this context because of their persistence. A solar flare lasts minutes. A coronal mass ejection might drive a geomagnetic storm for a day or two. But a coronal hole can blast Earth with high-speed wind for a week or more, and then come back 27 days later when the sun rotates it back into view. This creates prolonged periods of elevated geomagnetic activity. If there's any coupling effect, you'd expect it to be more apparent during these sustained disturbances rather than brief spikes. Some studies have looked at latency windows. The idea is that if solar wind influences seismicity, there might be a characteristic delay between the peak of geomagnetic activity and an increase in earthquake occurrence. Some papers claim to have found such windows, around 72 hours or so. Other papers find no such pattern. The data is messy. Earthquakes are rare events, statistically speaking, and teasing out weak correlations from rare events requires enormous datasets and careful statistical controls. It's easy to find spurious correlations if you're not rigorous. There's also the question of why seismologists, who are very smart and very rigorous, haven't latched onto this idea. Part of it is evidentiary. The burden of proof is high, and the evidence is weak, but part of it might also be disciplinary boundaries. Seismology and space physics are separate fields. They attend different conferences. They publish in different journals. They use different mathematical tools. A seismologist studying fault mechanics might never think to look at magnetospheric indices. A space physicist studying solar wind might never think about crustal stress. Bridging these fields is hard, and the motivation to do so is low when the conventional explanation that earthquakes are driven by tectonic stress and nothing else works perfectly well most of the time. But what if there's a signal hiding in the noise? What if the sun and earth are coupled in ways that are real but subtle, operating at the margins, influencing the timing of events that were going to happen anyway? What if a fault that's been building stress for decades, ready to slip, receives a tiny electromagnetic perturbation that advances the rupture by hours or days? That wouldn't be the sun causing the earthquake. It would be the sun influencing when an already primed earthquake happens. And that difference matters. The question isn't whether the sun controls Earth's seismicity. It doesn't. The question is whether the sun, through electromagnetic coupling, can modulate the timing of tectonic events in ways we haven't yet quantified. And if the answer is yes, even tentatively, even weakly, it opens a door to a much stranger view of how our planet interacts with its star. There's a concept in seismology that sounds like science fiction, but is firmly grounded in physics. It's called the antipodal effect. When an earthquake occurs, seismic waves radiate outward in all directions. Most of the energy dissipates relatively quickly, absorbed by the crust and mantle. But some of the energy travels through the entire body of the Earth. And when those waves converge on the opposite side of the planet, the antipode, they can focus. They can concentrate. And in some cases, they can trigger earthquakes at that distant location. The antipode of a point on Earth is the point directly opposite it on the globe. If you drilled straight through the center of the Earth from one point, you'd emerge at its antipode. For most locations on land, the antipode is in the ocean. The antipode of Japan, for instance, is somewhere in the South Atlantic. The antipode of Papua New Guinea is in the North Atlantic, near the Mid-Atlantic Ridge. And that's where this gets interesting. When the magnitude 6.5 earthquake struck near Papua New Guinea on December 22nd at a depth of 110 kilometers, it sent seismic waves careening through the mantle. Deep focus earthquakes are particularly efficient at transmitting energy over long distances, because the mantle at those depths is relatively uniform and acts like a waveguide. The waves travel with less scattering than they would through the heterogeneous crust. And when those waves reach the antipode, they arrive almost simultaneously from multiple directions, focusing their energy. Now, the Mid-Atlantic Ridge is one of the most seismically active tectonic boundaries on the planet. It's a divergent boundary, where the Eurasian and North American plates are pulling apart from the African and South American plates. New oceanic crust is constantly being created, as magma wells up from the mantle. It's a zone of weakness, fractured and faulted, under constant stress. It's also, conveniently, located near the antipode of Papua New Guinea. Here's the forecast, stated carefully. Based on the antipodal focusing effect and the statistical likelihood of stress transfer from the Papua New Guinea event, there is a non-negligible probability of a moderate earthquake, magnitude 5.5 to 6.5, occurring along the Mid-Atlantic Ridge in the coming days to weeks. This is not a deterministic prediction. Earthquakes are chaotic systems. You can't predict them with certainty, but you can assess probabilities, and the probability here is elevated. This isn't fringe science. Antipodal triggering has been studied for decades. There are documented cases where large earthquakes have been followed within hours to days by events at or near their antipodes. The mechanisms are debated. Some researchers think it's purely mechanical, the seismic waves providing the stress perturbation needed to trigger a fault already near failure. Others think there might be more complex interactions involving resonances in the Earth's normal modes, the whole Earth vibrations that occur after very large quakes. The Mid-Atlantic Ridge is a particularly good candidate for this kind of triggering because it's already under extensional stress. The plates are pulling apart, the crust is thin, the faults are active. It doesn't take much to push a fault over the edge when it's already loaded with stress. And the arrival of focused seismic energy from the opposite side of the planet might be just enough. Of course, even if an earthquake does occur along the Mid-Atlantic Ridge in the next few weeks, proving that it was triggered by the Papua New Guinea event is nearly impossible. Correlation isn't causation. The ridge has earthquakes all the time. Background seismicity is high, so you'd need to show that the timing and location were statistically unlikely given the baseline rates, and that the characteristics of the event were consistent with triggered seismicity. That's a high bar. But let's say it happens. Let's say a magnitude 6 quake hits the Mid-Atlantic Ridge 10 days from now. What would that mean? It would add to the growing body of evidence that Earth's fault systems are interconnected, that stress propagates across the globe in ways that are faster and more direct than the slow crawl of tectonic plates. It would suggest that the planet's crust is not a collection of isolated fault segments, but a coupled system, a network where a rupture in one location can influence the probability of rupture elsewhere. And if you start thinking about Earth as a coupled system, the door opens to even stranger possibilities. Because if stress can propagate across the globe through seismic waves, what about electromagnetic coupling? What about the ionosphere? What about the magnetosphere? What if the planet is not just mechanically coupled through seismic waves, but electromagnetically coupled through currents and fields? What if the sun, by perturbing the magnetosphere, is indirectly perturbing a global system that includes the crust? This is where conventional seismology starts to get uncomfortable, because once you allow for global coupling, for feedback loops, for interactions between subsystems that are normally studied in isolation, the models get complicated fast. The math gets hard. The predictions get fuzzy. And scientists, understandably, prefer models that are simple, testable, and robust. But the universe doesn't care what we prefer. If the planet is a coupled system, we have to deal with that complexity whether we like it or not. The antipodal forecast for the Mid-Atlantic Ridge is a test. If it happens, it's one more data point suggesting that global stress transfer is real. If it doesn't happen, well, the baseline probability wasn't certainty. Either way, the question remains: are we watching isolated events, or are we watching a planet-wide symphony of stress, energy, and release? Let's talk about the elephant in the room, or rather, the hole in the sundae, because there's this image, this striking, bizarre, almost absurd image from the SETI Institute showing the trans-equatorial coronal hole. And if you squint, if you tilt your head just right, it looks like Japan. The outline of the main islands, Honshu, Hokkaido, even the curve of the archipelago, it's there. And just days after this Japan-shaped hole opens on the sun, Japan experiences a magnitude 7.6 earthquake. Now, before we go any further, let's be absolutely clear. This is Paridolia. It's the human brain doing what it does best, finding patterns in randomness. We see faces in clouds. We see constellations in stars. We see maps in stains on the wall. The coronal hole doesn't actually look like Japan. It's a vague, shifting structure of plasma and magnetic fields that happens to have a certain geometry that, from one angle, in one image, bears a passing resemblance to an island nation. It means nothing, almost certainly. But it's the kind of coincidence that makes people uncomfortable. Because what if it doesn't mean nothing? What if there's some deeper connection, not between the shape and the quake, but between the solar activity and terrestrial events? What if the universe is trying to tell us something, and we're too entrenched in our models to listen? This is where science and speculation start to blur. This is the forbidden territory, where serious researchers fear to tread, because the moment you start asking questions like, is there a feedback loop between Earth and the Sun? You risk being labeled a crank. But let's ask it anyway. Is there? The standard model of solar-terrestrial interaction is one way. The Sun does things. Earth responds. The Sun emits radiation, solar wind, particles. Earth's atmosphere heats. The magnetosphere compresses. Auroras dance. Earth is passive. It doesn't talk back. It doesn't influence the sundae. The energy budget makes that clear. The Sun is 1,000,000 times more massive than Earth. It's a fusion reactor outputting 3.8 times 10 to the 26th watts. Earth is a tiny rock, bathed in a negligible fraction of that energy. The idea that Earth could influence solar processes is absurd. Or is it? Because Earth does have a magnetosphere. It does generate an electromagnetic environment that extends into space. When the solar wind interacts with Earth's magnetic field, it doesn't just compress the field, it creates structures. The bow shock, where the solar wind first encounters Earth's magnetic influence. The magnetopause, the boundary between the magnetosphere and interplanetary space. The magnetotail, stretching millions of kilometers downstream. These structures are dynamic. They generate waves, instabilities, currents. They radiate electromagnetic energy back into space. Could any of that energy make it back to the Sun? Probably not. The Sun is 150 million kilometers away. Electromagnetic waves dissipate. The solar wind is blowing outward, carrying energy away from the Sun, not toward it. But the Sun and Earth are connected by magnetic field lines. The Sun's magnetic field doesn't end at the solar surface. It extends throughout the solar system in the form of the interplanetary magnetic field carried by the solar wind. Earth sits embedded in this field, and when Earth's magnetosphere interacts with the interplanetary field, it can create disturbances that propagate along those field lines. Is it possible that information, encoded in magnetic fluctuations, could travel back up the field lines to the Sun? Is it possible that the Sun could, in some sense what's happening at Earth and respond? This is not standard astrophysics. This is speculative to the point of being wild. But it's not technically impossible. It's just extremely unlikely and completely unproven. And then there's the broader philosophical question. Do patterns mean something? The Japan-shaped coronal hole is one thing. But what about the timing of the earthquakes? What about the clustering of high-magnitude events during a period of intense solar activity? What about the historical correlations between solar cycles and seismicity that some researchers claim to have found? Some studies have looked at long-term trends. They've compared solar activity indices, things like sunspot numbers and solar flux, with global earthquake rates over decades or centuries. Some of these studies find correlations. Others find nothing. The quality of the data is variable. Earthquake catalogs get more complete as you approach the present, which introduces biases. Solar activity records are patchy the further back you go. Teasing out real signals from these messy data sets is a statistical nightmare. But let's say, for the sake of argument, that there is a real correlation. What would it mean? One interpretation is that it's causal but indirect. Solar activity influences Earth's electromagnetic environment, which subtly modulates the timing of tectonic events. Another interpretation is that it's not causal at all, but that both solar activity and tectonic activity are influenced by some third factor we haven't identified, a common driver. Or maybe it's just coincidence, the universe's way of reminding us that randomness can look like pattern when you stare at it long enough. There's also the question of intentionality, which is where we enter truly forbidden territory. When people see patterns like the Japan-shaped coronal hole, they sometimes start asking whether there's purpose behind it, whether the universe, or some intelligence within it, is communicating. This is not a scientific question. Science doesn't deal with purpose or intent, it deals with mechanisms and predictions. But it's a human question, and humans have been asking it for as long as we've looked up at the sky and wondered. The answer, almost certainly, is no. The universe is not sending us messages. Coronal holes form because of complex magnetohydrodynamic processes in the sun's corona. Earthquakes happen because of the slow, grinding movements of tectonic plates driven by mantle convection. These are physical processes, governed by physical laws, indifferent to human concerns or interpretations. The patterns we see are projections of our own minds, our desperate need to find meaning in chaos. But what if we're blinking? What if there are feedback loops, subtle couplings, interactions between subsystems that we've dismissed because they don't fit our current frameworks? What if the sun and earth are more entangled than we think, not through mystical forces or cosmic intent, but through physics we haven't yet fully mapped? What if the question isn't whether the universe is trying to tell us something, but whether we're asking the right questions to hear what the universe is actually doing? 2025 has been a strange year. Even before this massive trans-equatorial coronal hole showed up, things were happening that didn't quite fit the usual patterns. Space weather has been active, but not in the ways forecasters expected. Earth's seismicity has been elevated, but the distribution of events has been odd. And when you start pulling on these threads, you realize that the Sun-Earth system is noisier, more volatile, more unpredictable than the textbooks suggest. Start with the solar cycle itself. Solar cycle 25 reached its maximum earlier this year. Solar max is supposed to be a time of intense sunspot activity, frequent flares, lots of coronal mass ejections, and we got some of that. But the cycle has been behaving erratically. Some months have been quieter than expected. Other months have seen sudden spikes in activity. The transition from maximum to the declining phase has been choppy. And now, here we are in the declining phase, with one of the largest coronal holes in recent memory. Coronal holes are indeed more common during the declining phase, but this one stands out. Its size is exceptional. Its trans-equatorial geometry is rare. The SETI Institute noted that while coronal holes are expected, this particular structure is noteworthy for its extent and persistence. It's been visible for weeks now, rotating with the sun, blasting Earth every time it comes around. And the geomagnetic forecasts have reflected this. Space weather agencies have been issuing alerts for elevated storm risk, ranging from minor G1 storms to potentially strong G3 events. The magnetosphere has been taking a beating. The thing about solar cycles is that we've been tracking them systematically for less than 300 years. We have good sunspot records going back to the early 1700s. We have indirect proxies, things like tree ring, radiocarbon content, and ice core beryllium isotopes that tell us about solar activity going back thousands of years. But our direct, high-resolution observations of the sun's magnetic field, its corona, its complex structures, that's all very recent. We're essentially trying to understand an 11-year cycle with a few decades of truly detailed data. So, when the cycle does something unexpected, like producing this enormous trans-equatorial hole during the declining phase, we don't have enough historical context to know if it's genuinely anomalous or just rare. What we can say is that space weather forecasters didn't see this coming. The models predicted a relatively smooth transition from solar maximum to solar minimum. Instead, we got this. A structure so large and so well positioned that it's dominating the near-Earth space environment. The solar wind speed has been elevated for weeks. The interplanetary magnetic field strength has been higher than normal, and Earth's magnetosphere has been responding accordingly, compressing and relaxing in rhythm with the Sun's 27-day rotation period. Meanwhile, down on Earth, the seismicity picture has been equally unusual. The Pacific Ring of Fire is always active. It's a zone of subduction, collision, volcanism. Earthquakes are normal, but the clustering this year has been pronounced. Beyond the recent events in Japan and Papua New Guinea, there was that magnitude 8.8 quake in Russia earlier in the year. That was one of the largest earthquakes in recent decades. It struck in a region that doesn't always get that much attention, and it was a reminder that tectonic energy can build up and release anywhere along the ring. The Russian quake happened in August, magnitude 8.8. That's enormous. For context, the devastating Tohoku earthquake that struck Japan in 2011, the one that triggered the Fukushima nuclear disaster, was magnitude 9.1. So we're talking about an event that was maybe 40% as energetic as one of the most catastrophic earthquakes in modern history. And it happened in a region where major earthquakes are rare. The tectonic setting is complex, involving the subduction of the Pacific Plate beneath the Okhotsk microplate, but the area doesn't typically produce events of that magnitude. The fact that it did tells you something about the global budget of tectonic stress. The Earth has energy to release, and it's finding ways to do it. Volcanic activity has also been elevated. Multiple volcanoes around the Pacific Rim have been erupting or showing increased unrest. The Smithsonian Global Volcanism Program tracks this kind of activity, and their reports for 2025 show a higher than average number of eruptions. Volcanism and seismicity are related. Both are expressions of the same underlying tectonic processes. When you see an uptick in one, you often see an uptick in the other. Volcanoes erupt when magma, molten rock from the mantle, finds a pathway to the surface. That pathway is often created or widened by tectonic stress. When plates collide, one gets pushed down into the mantle, melts, and the buoyant magma rises. When plates pull apart, the pressure release allows mantle rock to melt. So volcanism is fundamentally tied to the same forces that drive earthquakes. If the Pacific Ring of Fire is experiencing elevated seismic activity, you'd expect elevated volcanic activity too. And that's exactly what we're seeing. There are currently multiple volcanoes in various states of eruption or unrest. In Indonesia, several volcanic systems are on alert. In the Philippines, monitoring agencies have raised warning levels. In Japan, volcanic tremor has been detected at several sites. In Central America, lava flows and ash plumes are being reported. None of this is individually unprecedented, but collectively, the level of activity suggests that something is happening at a systemic level. The crust is restless. Then there are the ionospheric anomalies. Some researchers have been monitoring disturbances in the ionosphere, particularly over tectonically active regions. The ionosphere is sensitive to a lot of things: solar radiation, geomagnetic activity, atmospheric waves from below. But there are studies suggesting that ionospheric disturbances can occur over fault zones in the days leading up to large earthquakes. The mechanisms aren't clear. It might be related to radon emission from the crust, which can ionize air molecules. It might be related to electromagnetic signals from stressed rocks, or it might be unrelated noise. The ionosphere is that layer of the atmosphere, roughly 80 to 600 kilometers up, where solar radiation strips electrons off atoms, creating a sea of charged particles. It's important for radio communications because it can reflect radio waves, allowing them to travel beyond the horizon. But it's also a sensitive detector of disturbances from both above and below. From above, solar flares and geomagnetic storms can dump energy into the ionosphere, heating it, changing its density, creating irregularities. From below, Atmospheric waves generated by weather systems, tsunamis, or even earthquakes can propagate upward and disturb the ionosphere. Some researchers have reported ionospheric anomalies appearing over earthquake epicenters days before the quake happens. If real, this would be huge. It would mean we might have a way to forecast earthquakes by monitoring the ionosphere. But the evidence is controversial. Many of the reported anomalies could be explained by other factors: solar activity, atmospheric variability, random fluctuations. And the statistical methods used to identify these precursors have been criticized for data mining, finding patterns after the fact rather than making genuine predictions. What's interesting is that some of these ionospheric anomalies have been correlated with solar wind streams. When high-speed wind from coronal holes hits Earth, it doesn't just affect the magnetosphere at high altitudes, it can drive currents and waves that propagate down into the ionosphere. And if the ionosphere is already being perturbed by pre-earthquake processes from below, you get a situation where solar activity and tectonic activity are both influencing the same region of the atmosphere. Untangling cause from effect in that scenario is nearly impossible with current data. Imagine you're trying to listen to a faint signal on a radio, but there's static from multiple sources. One source of static is local interference. Another is atmospheric noise. A third is cosmic background. How do you separate the signal from the noise when you have multiple overlapping sources? That's the problem with ionospheric earthquake precursors. Even if they're real, they're swamped by other effects. And when you add solar wind into the mix, creating its own ionospheric disturbances, the problem becomes even harder. There's also the question of non-linear dynamics. Large, complex systems like the Sun and Earth don't always behave in simple, linear ways. Small changes in one part of the system can have outsized effects elsewhere. Feedback loops can amplify signals. Resonances can emerge. The math gets complicated quickly, involving concepts like chaos theory, self-organized criticality, and emergent behavior. Seismologists are familiar with some of this. Earthquakes are classic examples of self-organized criticality. Faults build stress slowly until they reach a critical threshold, then release it all at once. But applying those concepts to the Sun-Earth system as a whole is challenging. Self-organized criticality is a concept from physics that describes systems that naturally evolve toward a critical state without external tuning. The classic example is a sand pile. As you add grains of sand, the pile grows until it reaches a critical slope. At that point, adding one more grain can trigger an avalanche of any size, from a few grains to a collapse of half the pile. The system is balanced at the edge of instability. Earthquakes work similarly. Stress accumulates on faults until it reaches a critical level, and then the fault slips. The size of the slip, the magnitude of the earthquake, depends on how much of the fault ruptures, which depends on the detailed stress distribution, which is impossible to know in advance. Now extend that thinking to the entire Sun-Earth system. What if multiple subsystems, solar magnetic fields, magnetospheric currents, ionospheric densities, crustal stresses, are all in states of self-organized criticality? What if they're all balanced near tipping points, and small perturbations in one can cascade into large changes in another? This is where the science gets genuinely hard, because modeling such systems requires enormous computational power and a level of detail we simply don't have. Are we living through a period where multiple subsystems, solar magnetic activity, magnetospheric dynamics, ionospheric disturbances, tectonic stress, are all fluctuating in ways that happen to overlap? Are these independent fluctuations, or are they coupled? And if they're coupled, what does that mean for prediction and understanding? The mainstream scientific answer is that these are mostly independent. Solar activity is driven by processes in the Sun. Tectonic activity is driven by processes in the Earth. They happen on the same planet, so there are some incidental interactions, but fundamentally, they're separate. The fringe answer is that we're missing something, that there are coupling mechanisms we haven't identified, that the planet and its star are part of a larger, integrated system. Both answers can't be fully true, but both might contain pieces of the truth. Maybe the mainstream is right that the coupling is weak and mostly irrelevant for practical purposes. Maybe the fringe is right that there are real effects hiding in the noise, waiting for better data and better models to reveal them. Or maybe the truth is somewhere in between, and what we're seeing in 2025 is a reminder that the universe is complex, noisy, and full of coincidences that look like patterns until you look closer and patterns that look like coincidences until you step back. The challenge is that we're trying to understand a system with incomplete information. We can measure some things very well: solar wind speed, magnetic field strength, earthquake magnitudes, volcanic eruption rates. But we can't measure everything. We can't measure the stress distribution along every fault. We can't measure the internal structure of every coronal hole. We can't measure every electromagnetic current flowing through the crust and atmosphere. So we build models with the data we have, and we hope those models capture the essential physics. But what if they don't? What if there are processes we're missing because we're not looking in the right places or asking the right questions? This is the uncomfortable space where science lives. The space between what we know and what we don't know. The space where patterns might be real or might be illusions. The space where the universe keeps surprising us, reminding us that our models are approximations, our understanding incomplete. And 2025, with its massive coronal hole and its restless crust and its ionospheric anomalies, is a year that's forcing us to sit in that uncomfortable space and wonder whether we're seeing something real or just seeing what we want to see. If there's one thing modern science is good at, it's generating data. We have satellites monitoring the sun 24/7. We have seismometers scattered across every continent and ocean floor. We have magnetometers, ionosphere sounders, GPS receivers, all feeding streams of data into databases that are growing exponentially. The problem isn't lack of information. The problem is making sense of it. Enter artificial intelligence. Machine learning algorithms are increasingly being used to sift through massive datasets, looking for patterns that human analysts might miss. In space weather, AI models are being trained to predict solar flares, coronal mass ejections, and geomagnetic storms based on solar imagery and magnetospheric data. In seismology, AI is being used to detect earthquakes in real time, classify waveforms, and even attempt probabilistic forecasting. The promise is tantalizing. If an AI could ingest data on solar activity, magnetospheric conditions, ionospheric disturbances, and seismic patterns, could it find correlations that humans have missed? Could it identify the subtle signals that link space weather to earthquakes? Could it forecast not just solar storms but their terrestrial consequences? The answer is maybe. But there are enormous challenges. The first is the problem of rare events. Earthquakes, especially large ones, are rare. You might get a few magnitude 7 quakes per year globally. Magnitude 8 quakes are even rarer. When you're trying to train a machine learning model, you need lots of examples. Rare events don't give you that. You can't train a robust model on a handful of data points. And the correlations you're looking for, if they exist, are probably weak. Weak correlations in rare events are statistically indistinguishable from noise unless you have enormous datasets spanning decades or centuries. The second challenge is causality versus correlation. AI is fantastic at finding correlations. It can spot patterns in data that no human would ever notice. But correlation doesn't imply causation. Just because solar wind streams and earthquakes sometimes coincide doesn't mean one causes the other. There might be a third factor. There might be no connection at all. An AI doesn't understand physics. It doesn't know the difference between a real physical mechanism and a spurious statistical association. It just sees the numbers. This is why AI in science needs human oversight. You can't just feed data into an algorithm and trust whatever it spits out. You need scientists who understand the underlying processes, to interpret the results, to test whether the correlations make physical sense, to design experiments and observations that can validate or refute the AI's predictions. In solar forecasting, AI has had some successes. Models can predict whether a solar active region is likely to produce a flare based on its magnetic configuration. They can forecast the arrival time of a coronal mass ejection based on its speed and trajectory. But these are relatively straightforward problems. The physics is well understood, the data is good, the timescales are short. Earthquake forecasting is harder, much harder. Earthquakes are triggered by the slow accumulation of tectonic stress over years or decades, released in seconds. The stress is invisible. You can't measure it directly. You can only infer it from GPS measurements of ground deformation, from seismicity patterns, from geodetic data. And even with all that data, predicting when and where a fault will rupture is notoriously difficult. Some seismologists argue it's fundamentally impossible because of the chaotic nature of the process. AI hasn't changed that. There have been attempts to use machine learning to forecast earthquakes, and some models have claimed success in retrospective analysis. But prospective forecasting, predicting earthquakes before they happen in a way that's useful, remains elusive. The models either have too many false positives, crying wolf constantly, or they miss events entirely. The skill, the ability to do better than random guessing, is marginal at best. Now, imagine trying to use AI to forecast earthquakes based on solar activity. You're combining two difficult problems. You're looking for a weak signal, if it exists, in noisy data. You're dealing with rare events. You're trying to bridge two different physical domains. It's a tall order. Could it be done? Maybe. If you had decades of high-quality, multi-parameter data, if you had physical models that constrained the search space, telling the AI what kinds of patterns to look for, if you had rigorous validation protocols. But we're not there yet. What we do have is the ability to monitor and document. We can watch the sun with unprecedented detail. We can track geomagnetic activity in real time. We can catalog earthquakes as they happen. And over time, those datasets will grow. Patterns, if they exist, will become clearer. Or they won't, and we'll conclude that the apparent correlations were illusions. The future of forecasting, whether it's solar storms or earthquakes or the coupling between them, lies in better observations and better models. We need more satellites monitoring the magnetosphere. We need denser networks of seismometers and GPS stations. We need computational models that can simulate the Sun-Earth system at high resolution. And we need the intellectual humility to admit when we don't know something, when the data isn't good enough, when the model is speculative. Because here's the uncomfortable truth. Despite all our technology, all our data, all our algorithms, the universe still surprises us. The sun still does things we don't expect. The earth still shakes in ways we can't predict. And the relationship between them, if there is one beyond the obvious electromagnetic interactions, remains a mystery. The massive transequatorial coronal hole is still there right now, rotating with the sun, blasting Earth with high-speed particles. The magnetosphere is compressed, geomagnetic storms are ongoing, and somewhere deep beneath the Pacific, tectonic plates are grinding, stress is accumulating, faults are creeping toward failure. Will the next big quake be in Japan? Along the mid-Atlantic ridge? Somewhere else entirely? We don't know. And the sun, blazing in the sky, isn't telling us. What we're left with is a story of complexity and uncertainty. A story of two massive systems, one stellar, one planetary, dancing around each other in ways we're only beginning to understand. The sun is open, Earth is stressed, and the universe, as always, is a far stranger and more interconnected place than our models suggest. We are witnesses to something. We just don't know yet what it means.